Okay, awesome. All right, so let's get started. I'm Tzu-Mao, as introduced, and I am currently working at UCSD with a bunch of awesome people. And today I'm just going to talk about classical computer graphics in the age of generative AI, which is probably what everyone is thinking right now. And there's like a lot of excitement and anxiety, right? So like this is a video I got from the Sora 2 website. And this is another one from the VO3 website. And this is another one from the Genie 3 website. This is another one. And there's like, when I was talking to some of my friends recently, and they are saying like, what are you teaching? And then I say, I'm teaching like computer graphics, like rendering stuff, programming, graphics pipeline, and I don't know, animation, geometry modeling. They're like, why are you still teaching this? Does it still matter? And that's what we're going to talk about today, okay? So, like, there are all these like generative pipeline, right? Like these like video generation. So how do they work exactly? So usually you have some input where there are text prompts and image prompts. And then these text prompts and image prompts, they go through like a big neural network. No one knows what's going on in there, but they're usually a transformer. And then the big neural network will give you like an image or a video. And this pipeline is like truly amazing, right? So it's very, very versatile. It can generate a lot of different images and videos, and it's very conceptually simple, right? You just feed it with a lot of data, and somehow they'll just give you magical results. And it fits very well with this narrative inside the AI world, which is like the bitter lesson. We'll get to that a little bit later. And then the inference is also like relatively fast. Like, of course, they're building like data centers of data centers, but inference time is like far faster than like the CPU farm with like thousands and hundreds of thousands of CPUs Pixar used to render their movies. So at this point, I feel that like we should already actually like stop a little bit and pause and think about why we're building these generative pipeline, right? So they seem to be very awesome, but what actually happened in practice? And so I was inspired by this talk by Aaron Hertzman a few years ago about like, what if CVPR is a graphics conference? And one possible reason that you could be building these generative pipeline would be that you're an AI person or you're a computer vision person, right? And you're like, oh, we know that intelligent beings are able to create arts and do great paintings and like draw animations, right? So an intelligent autonomous agent should be able to do the same thing. But I feel like this particular viewpoint doesn't resonate with me that much. And the other viewpoint actually resonate with me a lot more. And I don't know, I hope people here are similar to me, but it's fine if you're on the other part, okay? So a more computer graphics perspective of why we're building these generative pipeline would be that we're building algorithms, and these algorithms that are tools for art and expression. And importantly, like we graphics people develop systems and applications for artists to express themselves. We're not like, oh, building intelligence being just for the sake of building intelligence being. We are trying to help artists, okay? So let's try to imagine and envision what will the generative pipeline look like if there is actually an artist in there, right? So there's an artist and they want to like create some art, right? So they have some vision in their head, maybe a person flipping in a sunset. So, and then they try to create like text prompt and image prompt that match their vision. And then these things go through a big neural network. And then eventually you get a video, but you find that the generated video is completely different from what you envisioned from the beginning, right? And what's wrong with this? So the problem is that this generative pipeline is like the information density between the inputs and the outputs are just fundamentally different. And this is like a fundamentally unpredictable, ambiguous, and underdetermined mapping between the input and output. And there's just no way to fix it. Like, they'll get better. They'll generate more and more like realistic videos. They will adhere to your prompts better. But this pipeline is just fundamentally like there's not enough input to determine a unique output. Okay? So Let's, in contrast, look at the more classical computer graphics pipeline. Like maybe some of you have never seen this before, I don't know. So this is what actually happens. So like an artist, again, they have a vision, and what they will do is they'll find like a skybox, right? And these skies, they are modeling like atmospheric effects like Rayleigh scattering, Mie scattering, and things like that. And then you also like put the sun and ideally put it at the direction that is closer to the sunset. And then you also have these like procedural modeling for volumetric clouds, and you simulate like the multiple scattering inside the clouds, and you also have these like ocean wave model, and you have some procedural modeling for the land, and then you also have a character, and you also specify the animation of that character, right? And after you have all of these, you simply push the simulate button, and hopefully it will give you what you envisioned in the first place, right? And why could this actually achieve the vision of the artist? This is because like this like simulate between the inputs and the output is a predictable, well-defined function. It's not even a mapping, right? But it is a mapping, but it's even better than a mapping. Like there is a very well-defined behavior of what will happen given a certain kind of input. Okay. But on the other hand, like why are people very excited about the generative pipeline? It's because generative pipelines are usually more versatile, right? So this pipeline is not as versatile as the generative pipeline. So this brings me to my point, which is we should probably like try to get the best of the both worlds, right? It's not like one will replace the other, or I don't know, like it's either you die or I die kind of situation, right? So a probably better pipeline is that the artist has a vision, and they'll use both tools. They will use the generative pipeline to generate human understandable structure scenes. And if they want, they can also build a human understandable structure scene themselves, just like the old way, right? And then you push the same simulate button, which is predictable and understandable, and then hopefully you'll get the result you desire. Okay? And I claim that this is a predictable and versatile pipeline, so it has the best of both worlds. And also, it's kind of nice that it is backward compatible, right? So like if you just mask out the part with the neural network generating something, you can still have the old pipeline there and use it as usual. Okay? And the only thing I'm asking for is this like predictable, well-defined mapping. Okay, so that's the only thing I want. And I mentioned bitter lesson earlier, right? So that was like the strongest argument from the AI people. And this was from this Turing Award winner, Rich Sutton. And he said that general methods that leverage computation are ultimately the most effective. So this is from like Chess AI, for example. Like originally it was like Deep Blue used like a rule-based method, right? So it was kind of human interpretable, but not very scalable. And then like later data-driven method like the Go AI, like AlphaGo and AlphaZero, turned out to work better, and because they leverage data better. But like what is a general method is a very subjective thing. So I want to focus on this part of leverage computation. And graphics was actually pretty good at leveraging computation, right? So like if you look at like Toy Story from 1995, we were able to do video generation of 1.5 hours like 30 years ago, right? And back in the days, like they only needed like they could only have 366 objects in the film entirely. And if you fast forward like 20 years later, in Toy Story 4, they were able to put 10,000 objects in just one scene. And if you just fast forward a little bit more, in like modern Unreal Engine, we can put like 400 million swirl triangles in real time. So I claim that like classical graphics scale far better than modern diffusion models. Like you can just keep throwing more triangles, throwing more lights, throwing more things at it, and the modern renderer and simulator actually won't budge. They can do it pretty well. So like this scaling aspect is actually a pretty strong aspect of classical graphics. And in fact, classical graphics is really like a weird creature that maybe machine learning people are not that familiar with. And classical graphics is both human interpretable and scalable. So like you can understand what each part of the graphics, like you truly understand how each pixel is generated exactly, right? You can explain why this pixel is this color, and if it's not, it's debuggable. And compared to like something like a neural network, it's not really debuggable, right? And And I claim that this is like a very unique type of computation that doesn't appear that often in the history of computing. So let's talk about research then. So that was a little bit philosophical, right? So the research that I think we can do is, now we have this pipeline, right? So we have some data-driven model that maybe data-driven, maybe like procedural, but we have some model that can generate human understandable scenes, and they are structured. And then you can simulate them to get an image or a videos, and then you have a bunch of 2D or 3D training data, and then you can use these training data to backpropagate all the way to either like create 3D scenes or update the generative part of the pipeline. Okay? And so we have this data-driven optimization components in classical pipelines. And that leads to a lot of research opportunity. For example, if you just look at this part, this is like generative modeling of structured scenes, right? And it's actually a hot topic. I believe the other two keynotes are also about this topic, so I won't talk too much about this. But the more interesting thing is, if you look at the whole pipeline, there are a lot of other things that needs to be done and decided what to do. For example, if you look at the rightmost part, we need to design a loss function. Right? So what is the loss function? Is it just L2, or do we need something else? And if you look at the middle part, we have this simulate thing that we need to backpropagate through. So how do we compute the derivatives? How do we do it correctly and efficiently? And there's the actual part where once we have the derivatives, how do we use these derivatives to do the optimization? And that's not trivial either. Anyone who worked on animation will tell you that. And geometry processing. and again, if you take off of all this pipeline is fully backward compatible, right? So if you take out all the data-driven part, there's still the question of how do you do the simulation? So how do we make the classical graphics scale even better, support more types of primitives, and scale like even sublinearly to the number of components they have? So today, I'm just going to give you a few examples of our work that kind of like hopefully will fit into the pipeline I just talked about earlier. There will be like a principal loss function you can use for geometry optimization. There will be like automatic differentiation algorithm that is aware of discontinuities. And there will be an optimization algorithm that is aware of spatial coherence. And a common thing, don't worry about this too much, but a common thing about all three of them and a lot of other of our works is that we take insight from classical methods that provides guarantees of the pipeline, which is like a little bit more difficult to achieve in a data-driven pipeline. And these guarantees will help with predictability and understanding. And I'll get back to what this means later. So let's start with the first example of our work. This was done by a bunch of very talented students. And the task is we want to let the neural network predict a sign distance field. So our input is an n-dimensional point cloud representing a surface. So these green points are our input, and in this case, they represent this 2D star. But they could also represent like a 3D surface or even higher dimensional manifolds. And our output would be a neural network that takes x, the position, as input, and output f of x, where f of x is the distance to the closest surface, and this distance is signed, which means that it's positive if it's outside of the surface, outside of the object, and it will be negative if it's inside of the object. And hopefully it doesn't require too much convincing, but sign distance fields are pretty useful. They're useful for compressing geometry. So this is a paper from NVIDIA. They show that you can use it to represent very complicated geometry with very little memory. And bottom left is a paper from ours, actually. You can use it for inverse rendering because sign distance field can easily change the topology in the gradient-based optimization. So they are very useful for inverse recovery. And the bottom right, this one is a robotics paper. And you can use sign distance field for motion planning. You can use it to decide how to get from point A to point B for robots. And in this particular case, on the bottom right paper, they use a high dimensional SDF, like 7D or even higher. And let's look at how people used to do optimization for sign distance field, especially with neural networks. And the observation they have is like this. If you have a function f that is a sign distance field, then this function f will satisfy this equation called the iconal equation, which is almost everywhere, and which is saying that the norm of the gradient of f should be 1 almost everywhere. And they also need to be 0 at the boundary. This is just the requirement of a sign distance field. So at least at all these screen points, f of the screen points should be 0. Okay? And then, because we need to turn this into a gradient-based optimization problem to train the neural network, usually we turn this into some kind of L2 norms. And so you want to minimize, you want to take the gradient of f and then take the norm of it, and you want to like put a use it as a soft constraint to say it should be as close to 1 as possible. And then you also take the boundary of your surface, and then you say f at the boundary of your surface should be as close to 0 as possible. And then you try to like balance these two and minimize both of these. Okay? And but if we try to zoom in and just look at the simplest 1D case, this traditional laws using iconal equation will fail. So let's look at this 1D example where I have 2 boundary points. And this is just 1D, right? So the sign distance field will look like this dashed line. And it's negative inside, positive outside, and represent the distance to the closest green point. And here in the middle is a neural network that perfectly minimizes the traditional loss with the iconal equation and the boundary constraint. You can see, it actually so at the 2 boundary point, f is actually 0. And if you look at every point on the red curve, the slope of the curve, which is the norm of the gradient of f, is actually 1 almost everywhere except like at 3 points. Right? So this, the loss truly goes to the global minimum, but still it's still not our desired solution. So this is problematic, right? This indicates that there is something fundamentally wrong with this loss. And of course, this is just an advertisement. If you use our laws, it will actually get the correct result. And the problem is that mathematically, satisfying iconal equation does not guarantee that you get a distance field. So the logic goes from left to right, but it doesn't necessarily go from right to left. Okay? So, and this logical fallacy is even worse in the optimization because there are multiple global minimum of your loss function, and all these global minimum will drag with each other, and they create a highly non-convex optimization landscape, and because there are multiple solutions dragging the global gradient optimization. Okay. So how do we solve this? Our solution borrowed insight from classical geometry processing. So this is a paper from Keynote and some other also very smart folks in 2014, and it's called Geodesic in Heat. I won't talk too much about this paper in particular. If you're interested, you should read it. But the insight of this paper and also our paper is that there's this isomorphism between the simulation of heat and the measurement of distance between points, both in Euclidean space and in arbitrary metric. And so on the left, we have a heat field where the 2 red points, we want them to have heat of 1. That's the boundary condition. And then this heat field has some absorption coefficient lambda. And when it's small, the absorption isn't too large. And when the lambda is very large, it will absorb a lot of heat. And then on the right, we take the heat field, and then we take the log of the heat field, and then we flip it by taking the negative of that. And then we get the blue curve. And then the dashed black curve is the actual distance function. And you can see that as we increase the heat absorption lambda, the heat field, because it's absorbed very fast, right? So it will become more sharp, and the heat field and the negative log of the heat field will actually converge to the distance function. Okay, and I'll go through the math pretty quickly, so don't worry if it's gibberish. This is the actual key idea, and the math is just there because we need to get the loss function somehow. So physically, what it means is that if a heat field H minimizes the following energy. So this energy is an integral over your domain, and you measure the gradient of your heat field H, and then you take the norm of it, and then you square it, and then you plus the lambda squared times H, and then you want this to be as small as possible. And also, you have a boundary condition. You want H to be 1 at the boundary. And if you satisfy this heat simulation, then this heat simulation, when you take the negative log of it, and as you increase lambda to infinity, it will converge to distance field. Okay? And that's the guarantee I was talking about, right? So that geometric insights give you these kind of guarantees. And so at this point, it should be hopefully obvious what we are going to do. So we just directly use this integral heat energy as our loss. And so our method directly uses a heat energy as loss. And you have a neural network. It generates a function f of x. And so f of x is not the heat field yet. So we need to do a conversion. So a heat field taking negative log will become f. So we need to do the inverse. So f taking the negative exponent will become h. And once you have h, you can then put it into our loss function, right? So you want to minimize this integral, and you also want to satisfy the boundary condition. And from all of this, you can then just do the backpropagation to the weights of your neural network to try to satisfy this loss. Okay? And the guarantee is if you truly satisfy this loss, in the limit, as lambda goes to infinity, this loss will converge to an actual distance field. And this, like, we tried this and it works kind of surprisingly well. I didn't expect this to work, actually. And we tried to dig out why, but it gets a little bit technical. So I'll ask you to look at the paper, but the gist is that if you look at the gradient descent dynamics, this loss is actually like lead to a stable gradient descent dynamics, whereas Eikonal loss is unstable. And also, it's kind of perturbation robust. If you put a small perturbation of the solution to the Eikonal equation, the entire solution will change. But in our loss, the influence is local, and it drops exponentially fast. And finally, this one is the most interesting, I feel. Like this loss, you don't need any area regularization. It will just naturally penalize large surface area. And this is the usual, like, paper result that makes all the previous paper look kind of bad. But yeah, we tried this on a bunch of shapes, and it really works like surprisingly well. And all these three previous work are supposed to be already even better than Eikonal loss, but they still struggle reconstructing this bunny with like very complicated topology, and our method can recover the bunny pretty well. And we also tested on entire ShapeNet as well. And because we get a better distance field, we can do faster sphere tracing rendering as well. And here we're just visualizing the number of steps of sphere tracing. This is just like a rendering algorithm for rendering signed distance field. And if you have a better distance field, it leads to faster rendering. And really the takeaway I want to deliver is that these geometric insights are very useful for loss function design. And this, like, whenever you're doing a data-driven pipeline, you need a loss function. And how do you design a loss function? And if it's 3D related, maybe think about the geometry. All right, so let's go to the second work. This one is also pretty cool. This is done by all these also very talented students. The guy on the top left who refused to look at you, he is looking for jobs in case you are interested. And yeah, we're going to talk about differentiation and discontinuities. So the motivation is this. If you look at, like, so this is one task, one kind of arbitrary task we ask neural networks to do. We want to fit a 2D neural network to represent a very, 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 very high resolution image. And it looks fine at this view, but as we zoom in, you'll start to see that both instant NGP and ReLU fields, that are just fancy neural networks, start to have trouble representing discontinuities. Okay, so the references on the top left, and instant NGP and ReLU fields don't represent the discontinuity. They will blur out a little bit, and it gets worse as you zoom in more. Okay? So fundamentally, the problem is that neural networks are continuous function, right? So they, by definition, cannot represent discontinuities. And it's obvious when you look at what's happening at each layer. So it's either a matrix multiplication, which is continuous, or activation functions, which are usually continuous. And composition of continuous function are always continuous. So instead of neural networks, here's where I tell you shouldn't use it. And you should replace it with a general program with if-else statements that can represent discontinuities. For example, this is a function f, and it's a 2D function with a parameter theta. And if x is inside this green circle, then we return green. Otherwise, if x is inside this blue triangle, then we return blue. Otherwise, if it's a background, then we return white. And once we have this function, we focus on losses that are integrals. This just makes the math easier, trust me. So we focus on solving this problem of we have an integral over a loss function L, and L is this function that takes coordinate x and have some parameter theta, and we are going to integrate over the coordinate x. And this is an example. For example, you have a circle drawing function f, and you compare it to, and theta controls the horizontal translation of the circle, and you also have a target function I, and then you compare these two, you subtract them, and you take, let's say, L1 norm. So you take the absolute value of the difference. And you have this loss function L that you integrate over the entire image, and you want it to be as small as possible so that you can match your circle to the target circle. Okay? And this L function is still discontinuous, right? So there's the if condition is still there to test whether your point is inside the circle or not. And because these days, one of the best way to do optimization is gradient-based optimization. So we want to compute a gradient for optimization. So we have this integral, and then we want to compute the derivative with respect to theta. And so how do we do it? One way you can do it is you just throw this L function to PyTorch, right? And this is traditional automatic differentiation. And if you actually do it in this particular case, PyTorch will always output 0 for your derivatives. Probably not super surprising, right? Because inside those two return, there's nothing depends on theta. And the only thing in this function that depends on theta is in the if condition. And PyTorch doesn't do anything to the condition. So it will not optimize our shape. It will just like, you throw it to the optimizer, and then it does nothing. So it's hard to argue with the output of PyTorch, right? This seems like an impossible problem. It seems like PyTorch is doing the right thing, so what can we do? Let's actually observe what happens if we move the circle to the right, okay? And I made this fancy animation. So if you move the circle to the right, you can see that the integral of the loss actually changes like continuously. It's a smooth function with respect to theta. Does that make sense? Like if you move the circle to the right, you'll see that the black region increases smoothly, and the green region shrinks also smoothly. So while the integrand L is discontinuous with respect to theta, the integration of L over all of x is actually a smooth function with respect to theta. Okay? Interesting math, huh? And so if this is a smooth function, and you can prove that it's actually differentiable to theta. So if this is actually differentiable with respect to theta, why is PyTorch doing why is PyTorch doing that to all of us, right? So what is happening? So if you look at the infinitesimal change at this state, when I only move the circle to the rightward a little bit, all of the interesting things happen at this very thin infinitesimal circle where C evaluates to exactly 0 in my if condition. Right? So all the differential changes happen at this infinitesimal decision boundary. But unfortunately, because of this, and because of when we're evaluating integrals, usually these integrals do not have closed form, so we need to discretize the integral. So by discretization, we mean putting a bunch of these yellow points and evaluate the integral at these yellow points, and then we approximate the integral using these yellow points. And if you ask the derivative of all these yellow points, what is the derivative of L with respect to theta, they will only look at their infinitesimal neighborhood, and none of them will actually interact with this blue circle, right? So all the yellow points will just tell you that the derivative is 0 because what they see when the circle moves right is nothing changes around their infinitesimal neighborhood. Okay? So, and mathematically, there's like the chances that any of these yellow points hit the blue circle, the probability is exactly 0 because it's a measure 0 subset. So our solution to this problem at this point should be clear, right? So all you need to do is to actually put samples at these blue circles. And once you put these pink boundary samples, you can ask them, what is the derivative? And kind of intuitively, this pink circle, when the circle moves right a little bit, the pink circle will actually see in its infinitesimal neighborhood that there will be more green area, more black area and less green area. And then you just integrate over the blue circle, and then you'll get the answer. And this is kind of what a interesting small algorithm I found during my PhD. And we apply it to path tracing. But now this new work generalizes it to pretty much arbitrary programs. And you can prove this mathematically, which, again, I won't get into too much detail. When you have an integral, and then you have a derivative you want to evaluate of that integral, the derivative can be decomposed into two parts. The first part is pretty much just traditional automatic differentiation. So you take all these yellow samples, and then you ask them what are the derivatives with respect to theta. But there's an important second part of that derivatives, which is an integral over the boundary set over all the discontinuities. And inside this boundary integral, you evaluate the derivative of your loss by taking the condition C, and then you take the derivative with respect to theta divided by the norm of the C's derivative with respect to x, and you take negative. So this can be proved using implicit function theorem or something like that. And then this like decomposition of an integral coincides with distribution theory or something in fluid simulation called Reynolds transfer theorem. I just want to say that this is well justified mathematically, okay? And, but now we face the second big challenge. So I figured this out during my PhD, but I didn't figure out how to do this when I was graduating. And my student figured out how to do it. That's the fun part of academia. So if you have this like weird shape, there's actually only defined by an implicit function C. There's actually no easy way to do this to put your samples at exactly the location where C equals 0. Right, so what I want to do is I want to take this weird shape, and then I want to put my pink points exactly on the places where C equals 0, and that's not super easy. And here is where we, again, try to follow some geometric insights. And we apply insights from this math field called integral geometry. So I have an integral over some curve. And it can be open curve, it can be closed curve, doesn't matter. So I have an integration over a curve, and some integral geometry theorem, aka Crofton formula, tells us that the integral over this boundary is actually equivalent to an integral over all the lines. There are infinitely many lines in 2D space, right? And all these lines will intersect with these curves in some ways, and you can write it down as an integral over all of these curves, over all of these lines that intersect with the curves. And this generalizes to arbitrary manifolds in undimensional space. Okay? And this sounds very fancy, but if you look at the actual practical algorithm, it's kind of like a fancy edge detection algorithm. So what we're going to do in our practical algorithm is that we're just going to randomly sample a bunch of line segments in the space. Okay, so we have this weird curve, and we don't know how to put points on this curve, but we know how to put like lines in the space, right? And then, because we have access to the programs, we know that when we evaluate the two endpoints of each line segment, if they fall into different branches in our program, then they detect an edge. Right? So this is why it's called a fancy edge detection algorithm. So all these other line segments that didn't intersect with the curve is not important. And we only keep the ones where the two endpoints land on different branches. And now we have all these edges that we find that somehow we know there is an intersection with the curve. So what we're going to do is we're just going to start from the two ends of the line segment, and then we do a bisection, and then we can find the exact intersection between the lines and the curve. Right? And at this point, you can notice that we do have a well-distributed set of points on the curve already. So all we need to do next is we take all these pink points, and then we evaluate the derivatives, and then we integrate them over the curve, and we get the derivatives we want. Okay? And then draw rest of the all, right? So all you need to do next is to actually implement this inside a compiler that supports automatic differentiation. And in particular, this is just because it's a work from our group, we implemented our algorithm in this shading language called Slang. And it's something NVIDIA is pushing pretty hard these days, so maybe it will catch up. And you can see that it's a pretty standard shading language kind of format. It has loops, conditions, function calls, and all the things we expected. And then what we can do is now we can differentiate this, and our derivative will actually propagate through the if conditions and update the circle position, for example, from the previous example. And yeah, my students have a lot of fun making a lot of cool examples. For example, this is like a Voronoi mosaicing shader, and you can use it to match the Voronoi shader to arbitrary target shape on the right. And you can use it to fit a CSG tree to an existing mesh, and this will compress the mesh a little bit. So this is like an inverse CSG problem. And you can use it to make weird shadow arts. So this is optimizing for the shape of a lot of ellipsoid in the space. And these ellipsoid will project into different walls and give you different shadows. Cool. And one question we often get from people is, why can't we simply approximate the discontinuities, right? Why can't we take this discontinuity and then approximate using a smooth function? The problem is that it's very, very difficult to decide how much to blur. So if you blur too much, it becomes a completely different derivative, and it will not help your optimization. If you blur not enough, then because it's an integral, and we found that you need extremely high discretization resolution to capture the discontinuity. So there's this dilemma, and it's very difficult to resolve. But the boundary sampling solved both of the problems at the same time without any approximation. Cool. And again, takeaway is that classical method actually gives you some kind of structures. In this case, the if-else conditions, right, that are not modeled by the neural networks. And I love this quote from this movie director: the enemy of art is the absence of limitations. So neural networks try to model everything, and that's where they kind of fail also. Okay, the third work, and this is pretty cool as well. So optimization is hard, right? So if you try to build this classical graphic pipeline with optimization components, then you run into the problem that the gradient can be noisy, you have a non-convex loss landscape, and there is also that the loss landscape can be anisotropic, meaning that you need to move multiple parameters at once in order to decrease the loss. So people these days are very used to using Adam, but Adam will fail in this, again, very simple case. So I have a function and in 1D that I discretize into 1,000 parameters. So I have a theta, which is R1000. So on the left, the initial guess is theta is always 0 everywhere. And then I want to match it to a target, which is this weird signal. And again, it's a 1000D 1D signal. It's a 1,000 elements 1D signal. And And this is just like trying to benchmark how atoms do on some weird problems. And I designed a loss function, and I say the current theta should be as close to theta star on the right as possible. But I have a twist, which is I have this M matrix in the middle. That is a very noisy, although it's a positive definite matrix, but it's like all the components are drawn from some Gaussian distribution. Okay? And this loss is convex, right? So there's only one global minimum. So theoretically, if you just run atom long enough, it should give you the global optimum. But it doesn't, right? If you run it for even 5,000 iterations, you still get this like super noisy result. And it should converge after like maybe 5 million iterations, but we didn't have the patience to wait. And as we mentioned, like noise also makes things pretty bad. So this time we have an even simpler loss. It's just like an L2 norm between theta and theta star, but we inject Gaussian noise to the gradient. And again, atoms struggle strongly with a lot of noise. So how can we do better than atom? So the observation is that our target signals, like in graphics, like textures, volume, meshes, are often spatially smooth signals. And there's something we can do, which atom is not doing because it's a generic optimization algorithm, to use these spatially smooth properties. And one idea, which is not our idea, so this is actually already commonly done in a lot of classical optimization methods. So we can smooth the gradient spatially. Right? So the observation is that this blue curve is our current reconstruction, and then we're optimizing the blue curve to match our target, and the green arrows are the gradient informing how the curve should change to deform it to the target. And because we know that the final solution is smooth, one thing we can do is we can smooth the gradient spatially by applying this Gaussian filter. And it's a weighted average over all the nearby gradient. And by doing this, we enforce the evolution of the signal to be smooth, and we'll get a smooth signal. And this is well known. This is called Sobolev gradient descent or Laplacian smoothing gradient descent. But if you actually try this on our signal, you'll see this like kind of ringing artifacts because it over-smooths over the sharp corners of our target. Okay? So it is spatially smooth, but not spatially smooth everywhere. So that's a problem. So you either under-smooth or you over-smooth the results. So our twist to this very classical optimization algorithm is, well, we instead use an edge-aware filter. So these are filters that not only has a spatial weight, but they also have something called the range weight. So if, I'm trying to get the smooth result for this orange arrow at the middle, and then I only do the weighted average if the blue position of all the nearby green gradients are similar to my current position. That's the range weight. And this filter is a very classical computer graphics filter called the cross-bilateral filter. Okay? Cool? And the observation is that if you apply this bilateral filter or cross-bilateral filter, it will preserve these edges, right? Because if there are edges, then your bilateral filter will automatically avoid filtering the signal across the edges. And once you do this, our method actually preserves edges during optimization. And remember, atoms struggle even with 5,000 iterations, right? But if you combine our method with atom, it converges to pretty much the final result after 250 iterations. Okay? And if you line them up together, it's pretty significant, right? So atoms struggle even with 5,000 iterations, and Sobolev gradient descent also doesn't solve the problem. But if you have 250 iterations using this edge-aware filter, you get the final results very quick. Okay? And that was actually a little bit hacky, right? So we were worried that it actually isn't a proper optimization algorithm. But if you look a little bit deeper, it's actually a special case of something called a preconditioned gradient descent optimization method. So usual gradient descent doesn't have that P matrix. You just like adjust your parameter using the gradient and then multiply it by some step size lambda. But instead, you can use preconditioned gradient descent, which is you multiply the gradient with some arbitrary matrix P. As long as the matrix P is positive definite, the loss is always guaranteed to decrease for some existing step size lambda. Okay, so one possible choice is P is like the Gauss-Newton Hessian approximation, right? But that will be very expensive to compute, and it actually will not work for noisy gradient. So we need a different kind of P. And it turns out that for cross-bilateral filtering, P can be written in this form, which is D is the normalization for your filter so that the weights sum to 1, and then K is a positive definite symmetric matrix. And this P matrix, people have looked into it before. It is a non-symmetric real matrix with only real positive eigenvalues. So hopefully that gives you some sense that it approximates a positive definite matrix very well. And if you're interested, you can go into Payman Millenfar's paper in 2012, where they argue about this in more detail. When I found out about this, I was like extremely excited, but my students were like, it's detail, not important. So I don't know how you feel. We'll see. And this cross-bilateral filtering actually works for meshes as well. And I, again, will not go into detail of this, but there is this very nice paper from Justin, Keenan, and Adrian, and Chris. This is like a star team on this topic. And it's not my work, but they tell you how to do cross-bilateral filtering for meshes. And just some results, you can see that even with this like blurred projector images, you can see that like in this case, Atom give you like artifacts of noises, and then you have Sobolev gradient descent give you like these black dots, if you can see it. So it doesn't give you like very good results, but our method can recover the textures pretty well. And this is another example for optimizing the scattering coefficient and absorption coefficient inside the volume, and it converges much faster than Atom. And if you're not convinced that it converges faster, hopefully I can show the loss curve to convince you. So the red curve is ours, and the blue curve is Atom, and it converges much faster. And for meshes, it also preserves these sharp edges of meshes much better. And also in this case, there are some sharp corners in the face of the dragon, which Sobolev gradient descent doesn't work that well either. So takeaway, domain knowledge can significantly speed up optimization. And I don't know why machine learning people don't talk about it so much, but there's something called no free lunch theorem, which means that no optimization algorithm can be universally better than all the other ones. So usually you need to constrain yourself in your domain and design your optimization algorithm for your domain. And in graphics, often our targets are spatially smooth. So I hope that gives you some sense. Like a common thing of our work is that there are these insights from classical methods that give you this guarantee. Like in the SDF case, we have this convergence guarantee, and in the derivative case, we show that it matches the theorem of distribution theory, or Reynolds transfer theorem. And then on the right, it is a special case of precondition gradient descent. So my hope is that classical graphics will continue to act as a theory building tool, right? So you can design this input to output mapping. It can be ambiguous, it can be whatever, but there's always this like very deterministic and well-behaved and well-defined components in graphics where you map from 3D scene to images, image to edges, or doing physical simulation or doing sound simulation. And all these well-defined functions, we can explain them and understand them and predict what will happen with different kind of inputs. And let's rewind a little bit. Remember this video? This was supposed to be a plot twist because this was actually from the Houdini 21 trailer. And this was not from generative AI at all. This was a very classical physical simulation algorithm called material point method. And this was made by a human artist, okay, called Peter Senitra. And there was like no data-driven components at all here, okay? And yeah, you should check out this Houdini video. It's very cool. And again, like, let me show you some more classical graphics results. So these are the final projects from my Intro to Graphics course at UCSD. So these people don't have a lot of experience. They are not like professional artists. They made this by just, if you guys know, this is shader toy. So these are just pure GLSL fragment shaders. And they can make these like super amazing animation. And when I was grading the final project, I was like, oh my God, these people are amazing. And I had a lot of fun like looking at all these shaders our students make. So my point is that all of these like classical graphics results and all the art made by human are not worse at all, and I claim that they are a lot better than the videos generated by Sora 2, VO3, and Genie 3. I don't know how you think, but again, we might have forgotten how far we have gotten with computer graphics and how amazing it was. Right? Remember the first time you saw your computer graphics movies or whatever. It's truly amazing. And let's go to research. Right? So there's a sense that pure graphics is kind of dead or solved. And I claim it's not true. Like if you look at our recent work, so this is like as classical as it can get. Like we designed a variance reduction algorithm for multicolor rendering that accounts for vector integrals instead of scalar ones. Somehow no one has looked at this before. And we can show much better results than classical methods. And the community recognizes this. This is a best paper award. And if you want fancier stuff, sure, we have this newer paper that revisit radiosity. Like some people said it's a dead topic, but it's useful, right? Because now we have Gaussian splatting, and it's like a point cloud. You can simulate global illumination between the point clouds. And we show that you can get like far better geometry reconstruction by accounting for the light transport queue in the images. And this work from my student Wesley, they work on automatic rigging, but for capture hair strands. And somehow we're able to design something that is 100% neural network free, and there's no data. This is all handmade heuristics, and it works better than I thought. And this is from UCSC undergrad. He came to my office saying, I'm interested in plasma physics. I said, I know nothing about plasma physics, but he still insists in writing a paper. So we wrote a paper about modeling light sources in physical-based rendering using plasma physics by simulating like well-known PDE in those domains to model the light sources. And you can also just like combine older things, right? So there's this very popular rendering algorithm called Restir, and there's also this very popular rendering algorithm called bidirectional path tracing, and you can combine them, and then you get something far better. And you can also revisit classical insights, right? There's this guy called Eric Veitch, and his thesis was always the foundation of physically based rendering. And he has this path space, and we modified that path space so that we can use it to render differences between frames, and so that I can use it for animation and things alike. And this leads to like a completely different class of light transport algorithm you can design. And again, the community appreciates this. This is, again, another best paper award. So I often tell my students, even though they never believe me, I say nothing is ever solved if you look careful enough. And no insight you learn is useless in long term. Right? So even light transport simulation is not solved. So this brings me to my last dream. Like, so there's still this like not fully academically satisfying components in the pipeline. There's this neural network that's still somewhat not fully predictable and not fully understandable. So can we replace that neural network with a white box and interpretable program? And this is not a paper. This is just my random experiments I wrote with NumPy. I tried to vibe code it, but it didn't work. So I have to write it by hand. So, diffusion model is all about adding noise and denoising images. And they denoise the image usually using neural networks. But instead, how about we replace the denoising component using classical denoising algorithms? So I have a noisy image, and I have another clean input image. And then I can grab patches from my input image and copy paste it to the noisy image and use this copy pasting to denoise the image. This is called non-local means denoising. And then I just try to use this denoising component inside the diffusion model. So I start from pure noise, and then I copy patches and I add noise. I copy patches, I add noise. And eventually I recover like some very classical texture synthesis algorithm, right? So, but this is a diffusion model. This is a single image, neural network-free, data-free diffusion model. So I hope that like more and more work like this appear, where some people have tried similar stuff before. I listed some of the references here, but I hope more and more people try to do this. We try to like explain and build theory of data-driven pipeline and try to explain what exactly they're doing. And this brings me to my last point. I'm almost done. Bear with me. So it can feel like very overwhelming and annoying to some sense that like there's so many things. There's Llama 4, Gemini 2.5, Genie 3, DeepSeek, Copilot, Cloud Sonnet, VO3, Midjourney, GPT-5, Sora 2, Qwen 3. I'm probably missing like 50 of them here, right? And this is like an entire red ocean where everyone is kind of doing the same thing. There's a strong homogeneity over the space. And my advice is to all of you, don't have to listen, but think about it, is to be curious and be critical. And it's very easy to be overwhelmed and shut down looking at all of these, right? But if you are curious about them, like just don't be as cynical as me, but like be curious about them, but also be critical. And you should have fun when doing research, and you should like tackle challenging problems, and also like you want to fight with the homogeneity, right? We are researchers, we want to do something different. So you want to be different and even be weird. Like so I said don't be as cynical as me, but be as weird as me, okay? So be weird. And it's possible that classical graphics is a kind of blue ocean that you don't have to compete with all these people, right? And there are a lot of things that are not solved and they're interesting and they're very satisfying to play with. And we need more people working on these things. All right, so that ends my talk. My ending remark is you should remember there are always human beings in your pipeline. That human beings can be an artist, it can be a researcher, it can be just random students sitting down there. But remember, like, it's very easy to forget that you are building algorithm or whatever intelligence being that can destroy the world, but there are humans, okay? And also, we should always remember to check out our website for the papers that are mentioned. All right, thank you.